What did the rhombus say to the square? Lean on me. You see a rhombus, looks like a leaned over square. You got it? Okay. All right. So now we're talking about special parallelograms. You learned about these in 6th grade. Actually, probably before. You did learn the word rhombus. You did learn the word parallelogram, rectangle, square. Though you already knew some of those words actually from elementary. Well, some of the properties. Let's start first with rectangles. If a quadrilateral is a rectangle, then it is a parallelogram because opposite sides have to be parallel. A rectangle has all the properties of a parallelogram plus a few more. A rectangle is an equiangular parallelogram. So the sides are not necessarily equal. They could be if the rectangle is a square. But for sure, all of the angles are equal. They all equal 90 degrees. Now, if a parallelogram is a rectangle, then its diagonals are congruent. So that we'll be using that to show that some things are rectangles and solving some problems. Now, rhombuses or rhombi, I've seen both pluralizations. If a quadrilateral is a rhombus, then it is also a parallelogram. So we're talking about these special parallelograms. A rhombus is an equilateral parallelogram, so all the sides are always equal. If a parallelogram is a rhombus, then its diagonals are perpendicular. So remember how kites had perpendicular diagonals, although they're not parallelograms. Rhombuses also have perpendicular diagonals. And if a parallelogram is a rhombus, then each diagonal bisects a pair of opposite angles. So let's go ahead and then we've got squares. Now, if a quadrilateral is a square, then it is a rectangle and a rhombus and a parallelogram. So it has all the properties of the three. Squares are equilateral, they're equiangular, the diagonals are perpendicular, just like for a rhombus. Each diagonal bisects the opposite, 90-degree angles into 45, and remember, rectangles bisect. And the diagonals are congruent. So, let's take a look at the group of quadrilaterals we've been studying. First of all, we have over here kind of some just irregular quadrilaterals because they're not equilateral or equiangular. We also studied some other special quadrilaterals, including the trapezoid and the kite. And just this last lesson, we learned about parallelograms, and now we're getting even deeper into special parallelograms, the rectangle, the rhombus, and the square. So if you look at this, let's say I take these two right here, those are definitely quadrilaterals, but they're not really one of the special groups we studied. These are trapezoids, which are also quadrilaterals. This is a kite, which is also a quadrilateral. This is a parallelogram, which is also a quadrilateral. This is a rectangle, which is also a parallelogram, which is also a quadrilateral. And this is a rhombus, which is also a parallelogram, which is also a quadrilateral. And finally, this is a square, which is also a rectangle, which is also a rhombus, which is also a parallelogram, which is also a quadrilateral. So the square fits into most of the groups in the quadrilaterals. Now let's go ahead and take an example. We're saying the vertices of a square PQRS, and they give them to you here, and we want to show that the diagonals of square PQRS are congruent perpendicular bisectors of each other. So for a square, the diagonals have to be congruent because squares count as rectangles. The diagonals have to be perpendicular because they count as rhombuses. So let's go ahead and see what we got. I went ahead and did the points in order just to make sure I knew where they are. P, Q, R, and that should be an S there. And the first thing I decided to find was the slope. So the diagonal for PR, I just went ahead and used the points up here. -5 minus 0 and 7 minus -4, and I got -5 over 11ths. Then I'm going to find diagonal QS. So diagonal QS, the slope is -8 minus 3, -1 minus 4, so I get -11 over -5, which is positive 11/5. Since the slopes are negative reciprocals, the diagonals are perpendicular. So far we got the perpendicular. How do we know they're bisectors? I decided to go ahead and use the midpoint. So if I find the midpoint of PR, I just use the two endpoints and average them to get the new midpoint, 3/2 and -5/2. It's not necessary to get really, change these to mixed numbers. I'm just trying to compare to see if they're equal. Now I'm going to find the midpoint of QS. And when I substitute these values in for x1 and x2 and y1 and y2, I get the same midpoint. Since these two have exactly the same midpoint, and they are perpendicular, then they are perpendicular bisectors of each other. Now, one thing I didn't leave a lot of room on here, so you might need an extra piece of paper or something. I actually need to show these are congruent, and I haven't done that on these notes. So I'm going to find the distance of the first diagonal, which is PR right there. So PR, and the way I do that is I do the square root of, using the distance formula, x2 minus x1 squared plus y2 minus y1 squared. So for PR, x2, 7 minus -4. 7 minus -4. I'm going to put parentheses around that, square it, plus, and I'm still doing PR. So now y2 minus y1, -5 minus 0 squared. And 7 minus -4 squared is going to be 11 squared plus, that's an equals there, 5 squared. Actually, I should say -5 squared because it's really a -5 squared. And put a square root all over that. I'm going to go ahead, I can simplify this, I'll square them out, but I'm not going to do a lot more because I only need to show that they're equal. I don't need to find the actual values. So I have the square root of 121 plus 25. Let me find the diagonal of QS. So that's the other diagonal here. And so I'm going to use the same formula. y2 minus y1 x2 minus x1, -1 minus 4. -1 minus 4 squared plus y2 minus y1, QS, -8 minus 3 squared. And put the square root all over that. And I'll get d of QS, the distance of that, it's going to be -5 squared plus -11 in parentheses squared. Now, since the negatives are in the parentheses and are being squared, we'll actually get a positive. So I'll have 25 plus 121. So you can see that actually both of these diagonals are congruent. So I have shown that they are perpendicular, they are bisectors, and they are congruent. So since they're congruent, it has to be a rectangle. Since they are perpendicular, it must be a rhombus. And of course, they're going to end up being perpendicular bisectors. Now on example 2, first of all, I accidentally left a 1 as somehow it got cut off on the printout. So this is supposed to be 12y for this angle. Since it's a rhombus, we know a couple things. All the sides are congruent and the rhombuses, the diagonals, are perpendicular to each other. So let me start with the congruent sides. I know that 4x plus 15 has to equal 7x plus 2 because the sides are congruent. I'll go ahead and solve for x, and I get 15 equals 3x plus 2. Subtract 2 from both sides, and I get 13 equals 3x, or x is 13/3. Now, if I find CD here, that means that's going to be the same as AB. So let me find CD. I substitute in 13/3 in for x, 7 times 13/3 over 3 plus 2. I get 91/3 plus 2, and I went ahead and used the calculator, and I get 32.3 bar. So if that is the size of CD, the length of CD, it's also going to be the length of AB because all sides on a rhombus are congruent. Now let's take a look at the angles. I know this angle right here is a right angle. So I say 12y equals 90, and I solve for y, and I get 7.5. Then I realize I'm looking for angle ABC, which is this angle right here. And now that I know y, I can probably find that angle in there. So let me go ahead and redraw. You might see there's actually a shape here. It's a triangle right there. And so that's a triangle I'm going to redraw. And here's point A, point B, and point C. All right. So this, once I substitute in 7.5 in for y, I get 4 times 7.5 minus 1, 30 minus 1, or 29. So that's 29 degrees, and that's 29 degrees. This is an isosceles because both these sides are congruent since it's a rhombus. And so it's an isosceles triangle, and I can solve for that angle by saying 29 plus 29 plus this angle must equal 180. 29 plus 29 is 58. Subtract 58 from both sides, and I get the measure of angle ABC is 122.